Okay, so now successive transformations. So this is like the parts we've missed out in questions where it says you've got a matrix transformation followed by another transformation. So basically, like I've written here, if transformation T is applied to a matrix M and it's followed by another transformation U, you'd think, oh, so T is first, then U, and that's the order that it's applied in. But actually you do it in like reverse order, so like the second transformation goes first. So instead of TUM, you'd multiply UTM. Now, like, why is this? So if you go back to like functions, like if we have f of g of x, the composite function, basically this is the inner function, and this inner function we're applying f to. So like it's basically f of g of x. So if there were transformations, like g of x would be the first transformation that it's happening to, and then after that we're having the f transformation. So we do it in like this reverse order of like the second transformation goes first in the multiplication, then we have the first one. And the transformation always goes before the matrix. So it's not going to be like m in front, then ut, or mtu, which we know is going to be like wrong anyway. The transformation always comes first. And that's the same with like multiplying a matrix by a point. So if we have a matrix like A, B, C, D, and we're multiplying it by x, y, we don't do x, y, then A, B, C, D. We do A, B, C, D first, then x, y. So the transformations always go first in the multiplication. So in this case, even though M is a matrix, the transformation matrices come before M. So now let's try the questions we missed out before. So this was the triangle question where we said we'll do part B and C later. So I think let's just make this text a bit more smaller. Alright, so part B. The transformation V consists of a stretch scale factor 3 parallel to the x-axis with the y-axis invariant. Okay, so let's just write down V first. So we did earlier that a stretch was A0, 0B, where the A0 bit is parallel to the x-axis, and that bit is parallel to the y-axis. So V consists of a stretch scale factor 3 parallel to the x-axis. So in this case, A is 3 because that's the one parallel to the x-axis. It's going to be 3, 0, and stretch scale factor minus 2 parallel to the y-axis. So that's going to be 0, minus 2. So the transformation V is represented by the matrix Q, so we should write Q is equal to that. So that's part B done. Part C. Given that U followed by V is a transformation W, which is represented by the matrix R, find the matrix R. So transformation U was this matrix P over here, and the matrix P, we worked out P is equal to 1. So we can write P is equal to P, which is 1, minus 1, 2P is 2, 3P is 3. So P is that. So the transformation U is the matrix P, followed by V. So because we're following by V, remember V goes first. So V was represented by the matrix Q, so what we're going to do is 3, 0, 0 minus 2, multiplied by 1 minus 1, 2, 3. And this gives the matrix R. So now we just multiply the matrices together. So 3 times 1 is 3, and then 0 minus 1 is 0, so we're going to get 3 minus 6. So our matrix for R is 3, 6, 2, minus 6. So now let's just check if that's correct. So the first one, part B, 3, 0, 0, minus 2, 3, 0, 0, minus 2, that. And then part C, 3, 2, 6, minus 6, 3, 2, 6, minus 6, so that's correct. Right, now the next question was this one. So this was from the last video on 2D rotations, so part C. Given that U followed by V is a transformation T, which is represented by the matrix C, find the matrix C. Right, so U followed by V, so V is represented by a matrix B, and we found matrix B was this over here. So U followed by V is going to be the matrix for V first, which is B, and then multiply it by U, and U was matrix A. So we're going to multiply BA. So B was 0, minus 1, minus 1, 0. And multiplying it by A, which was minus half root 3 over 2, minus root 3 over 2, minus half. So 0 and minus half is 0, and then minus 1 times root 3 over 2 is minus root 3 over 2. So that's going to give us minus root 3 over 2 and root 3 over 2. And this is our matrix C. Now part D. Show that there is a real number k for which the point 1k is invariant under T. Right, now T was represented by the matrix C. So invariant point, remember that's like the transformation matrix multiplied by xy. It's invariant, so we just get xy. So the point in this case, x is 1 and then y is k. So the matrix C, so minus root 3 over 2, a half, root 3 over 2, multiplied by this coordinate 1k will give us 1k. And we have to show that there is a real number k for which this is true. So let's multiply out. So if we multiply this row and this column, we'll get the one over here. So what we'll get is minus root 3 over 2 times 1, which is minus root 3 over 2, plus a half k, and that is equal to 1. So that suggests that k over 2 is equal to 1 plus root 3 over 2, which is 2 plus root 3 over 2. So therefore k is equal to 2 plus root 3. Okay, now we'll do the other multiplication, so this row by this column to give us k. So what we'll get is a half plus root 3 over 2k, and that is equal to k. Now we'll subtract root 3 over 2k from both sides, so we get a half is equal to 2 minus root 3 over 2k, and now we'll just divide everything by 2 minus root 3 over 2, so we get a half divided by 2 minus root 3 over 2 is equal to 2 plus root 3, yep, so k is equal to 2 plus root 3, that's the same, so the same value of k, therefore there is a real number for k for which this is true. Okay, now let's check the mark scheme. So we've done part B already. Now part C, minus root 3 over 2, a half root 3 over 2, minus root 3 over 2, a half root 3 over 2, yep. And D, k is 2 plus root 3, yep. That's what we got. So yeah, I hope this was helpful. In the next video we'll probably be finishing off, or maybe have one more after that, and that's on all the 3D rotations and 3D reflections and stuff. So I hope this was helpful. Bye bye.